So now that we looked at the implementation of the interpreter pattern, let's go ahead and talk about some other considerations to think about when you decide to apply this pattern or not. We'll start with some of the positive consequences. Simple grammars are easy to represent, change, and extend by using the interpreter pattern. This particular example, of course, was focused on arithmetic expressions using a grammar that removed left recursion in order to make it work properly with the parsing that we applied with the interpreter pattern. In this particular approach, all the rules are represented by distinct classes in an orderly and consistent manner. If you take a look, you can see, for example, we have the expert hierarchy here with various methods like interpret and build, and it all just flows very nicely from the way in which that grammar is defined. If you want to add another rule to the grammar, you simply add another class. So if we decided we wanted to add in something above and beyond the add or multiply expers like modulus operations, that would be a simple thing to do. However, when you start getting complicated grammars, such as the grammar for C++ expressions, which is very complicated, believe me, then you can end up with a very unwieldy approach that may be hard to implement by using the interpreter pattern in the manner we've described here, because you end up with lots of classes. Many of those classes are interdependent and therefore tedious and error prone to develop and evolve. In that particular case, you're probably much, much better off using some kind of parser generator or grammar processing program, such as Antler or Java CC if you're a Java developer, such as Lex and Yak if you're an old school C developer, such as Flex and Bison if you're a newer C and C++ developer. And these parser generators, as they're often called, can be used to handle these more complex grammars in often a more efficient way. There's also a number of implementation considerations to think about when you apply this pattern. For example, how should you apply it? One obvious way, which we've done in our example here for the post-order interpreter, is to express the language rules with one rule per class. So literal translations are expressed as terminal expressions, things like the number expr, for example. And then the binary and unary nodes are expressed as non-terminal expressions. And so this is all handled in a very clean and convenient way. This approach can yield a large number of classes, but the good news is that the classes that you define mimic the grammar. So as long as you can have a tractable and obviously well-crafted grammar that's easy to understand and intuitive, then the implementation flows nicely from that. Another approach, which I also have implementations for, is to apply something called operator precedence parsing. And in this particular case, rather than having to write all these different classes, you instead build an operator precedence parser. And this is particularly useful if you're trying to do things like build a parse tree from in-order expressions, which are a lot more complicated to parse and process than the post-order expressions that we did with our post-order interpreter. So you could read about operator precedence parsing at the link down below here. And then this particular approach has the benefit that there are fewer classes involved, but the software design doesn't mimic the grammar in quite an obvious way. I actually have written an operator precedence parser generator program, which I, believe it or not, I actually wrote this in 1989. So over 30 years ago from the time of this video. And I actually used it to generate the various elements that were needed for an operator precedence version of the interpreter for in-order interpretation. So you might want to take a look at that implementation as well. There's a number of known uses of the interpreter pattern. The Gang of Four book gives a bunch of examples, from text editors to web browsers to the tech typesetting program. Various compilers, such as Smalltalk compilers, have applied the interpreter pattern. And there's also some interesting examples of applying interpreter for doing regular expression parsing. You can take a look at the link at the bottom of this slide to see some examples of that. Regular expressions obviously are very powerful ways of searching for patterns and wildcards in text strings. So you might take a look at this to see, for example, how Java defines the regular expression package. And C and C++ do similar things as well. So to summarize how we've applied the interpreter pattern thus far, we've used it to take the user input that comes in the form of a string and then to automatically convert that into a parse tree. And then when we talk about the builder pattern, which we'll go to next, you can see how you can use the parse tree created by the interpreter in order to build a composite expression tree, which is really the actual internal representation that's applied by our expression tree processing app case study. And you can think of Builder as being a creational pattern that's used in conjunction with an interpreter as part of a so-called pattern compound in order to carry out this more advanced processing stage.